Okay, hey, today we are going to be exploring hydrolysis, a little bit of review from Bronsted-Lowry theory, and then we're going to do a couple of the like metal salts hydrolysis problems that can be kind of tricky for some students. So we are going to try our best here. And again, if you need help, you can just pause this video. There's a ton of other videos on YouTube if you look up hydrolysis of metal salts. But anyways, let's get started. So today what you should understand, first of all, is that an acid is a proton donor and a base is a proton acceptor. So in this equation, we can kind of tell what's what. So let me get my pen going here. And you can see that, see how this is ClO minus. So we know this is going to act as a base. So this is going to accept a proton. And that this guy right here is going to be a proton donor. And so it's going to be OH minus. And this would be my base. This would be its conjugate acid. This would be an acid. And this would be its conjugate base. So this is like for the very first day when we did acid-base definitions. That's how we were able to figure this out. Okay, so on this next one, you can see that this guy has an extra H, so we're going to get NH3 plus, and it's going to get H3O plus. And so this is acting as an acid. This would be acting as its conjugate base. This would be a base, and this would be its conjugate acid. I'll do one more, and then we're going to skip this one. Skip it. So we have SO4 minus 2, and then we have H3O plus, and it's the same thing as the one above. This is my acid. This is my base. This is my conjugate base, and this would be my conjugate acid. So when I'm doing these, the biggest thing is to look where the H's are and know that someone is going to be a loser, someone is going to be a gainer, and that's just what happens with those ones. All right, so now what you have to know is you have to know that the relative strength of the bases are going to determine the net direction of the equilibrium. So for example, if I have, I'll just give you this example on the next page here. So if I have HCl plus, let's just do SO4 minus 2. And I'm just giving you an example of this one just so you can see. So you would get HSO4 minus plus Cl minus, right? This is going to lose an H. This is going to gain an H. It's deficient. And now you have HSO4. So just to clarify right here, so this is my acid. This would be my base. This would be its conjugate acid. This would be its base. What we need to figure out is, this would be its conjugate base. We need to figure out which direction does this go. Does it lie more on this side or does it lie on this side? And the way you can do that is you decide which side has the stronger acid. So you're going to look on the previous chart, which when I do this, I feel like I'm going to lose my drawing. Hopefully not. Let's see. Let's see if I can go back up. Okay, yeah, so we're going to go back here. You can see that HCl is at the very top. So this is the strongest acid. And then over here, you can see that HSO4, that's this guy right over here. If I mark it right here, you can see that it's not as strong. So it always goes from strong, this guy, to weak. And so this equilibrium would lie on the right, meaning that there's more products than reactants. Okay, so that's just an example of just like understanding that strong acids have weak conjugates, and weak acids have stronger conjugates, meaning that there's just more stuff that goes on there if they're weak. All right, now metal salts. Okay, when you take an acid plus a base, so let me just give you an example of this. So we have HCl plus NaOH. You would get, it's double replacement. These are called water formers. You get NaCl plus H2O. You always get a salt plus water. Okay, so the salt, the base always provides the cation. The anion always comes from the acid. So for example, if I was to figure out like Ki, so we know that the products, like if this was a salt, the products of this would have been, like the reactants would have been KOH and HI, because these guys come together and form the salt, and then OH and H come together and form water. So you always get salt and water. So we often refer to this as this is the parent base, this is the parent acid. And that's going to tell us like a lot about it, because like you're going to be able to tell if the salt has the ability to hydrolyze water based on what parents it has, like what are the things that make it. So anyways, when you add an acid plus a base, you always get a salt plus water. This salt determines whether or not it acts as an acid or base in the reaction. Okay, so hydrolysis is just that. This is the splitting of water, or, splitting of water of some salts, because the fact is the salts have, they're basically stronger conjugates. So for example, here's what I'm talking about. So this is a strong base right here, right? So this is NaOH. So strong bases are like group 1 and part of group 2. And this is a weak acid. It's not one of the 7 strong. So when they come together, remember the cation comes from the base right here. The anion comes from the acid. This doesn't have an effect on water, because strong acids, their conjugates are super weak. But weak acids like this have relatively strong conjugates. And what happens is this actually is like, sweet, I'm a base and I'm in water. Guess what I'm going to do? I'm going to accept protons. And so what you're going to get is you're going to get this reaction that takes place, because this is the conjugate base of a weak acid. It's going to be not super strong, but it's still going to be strong enough where you are going to get just a little bit of this. And if you get a little bit of that, it actually is a base. And so salts of strong acids, strong bases, they don't do anything. They're just pH of 7. But salts of weak acids and weak bases, well, they hydrolyze water at some point. And so you have to kind of understand the structure to figure it out. Now, this is also important that you understand that, oops, let me go back. Go back, or I'm just keep going the wrong direction. Wow. Okay. Now this is actually super important. So Kw, that's 10 to the negative 14th. Remember that that's like a definition of water, is that basically the H plus times the OH minus would equal 10 to the negative 14th. But what we found is that if you take Ka times Kb, you get Kw. This is kind of a definition of kind of how they're related to each other. So if I wanted to know Kb, Kb is actually equal to Kw divided by Ka, or Ka is Kw divided by Kb. So you use this often to go between the two. So if I know the Ka for this, and I do, like I know the Ka for this, the Kb for this guy right here is just Kw divided by Ka. So there's an appendix in the back of your book, Appendix D, that has all the Kas listed, and you can look that up. And then to find the Kb of its conjugate base, you just do this cool formula right here, which I'll show you in a second. Okay, so let's keep going. All right, so because of the fact that salts can produce acid or basic salts. So first off, if it is a strong acid plus a strong base, so this would be like something like HCl plus NaOH, right? Your salt would be NaCl, and that is neutral. This doesn't do anything because Cl is the conjugate base of a super strong acid, and then same with Na plus. So what happens is no pH, okay? But if you have a strong acid and a strong base and a weak acid, what happens is this has a relatively strong conjugate base, so the pH would be greater than 7. So an example of this would be like KF, where KOH is a strong acid and HF is a strong base, and HF is a weak acid. So this would act as a relatively strong conjugate base. Another example would be if you have a strong acid and a weak base, the pH would be less than 7. Okay, so an example of this might be something like NH4Cl. So this guy, the Cl comes from HCl, and this comes from NH4OH, which is a weak base. And so what actually happens is this can actually act as a weak acid, because weak bases have strong conjugates. I know that's super weird, but that's something that you have to get used to. And then finally, it just depends for this one. It depends on the Ka or Kb. if it's both a weak acid and weak base, the one with the stronger Ka or stronger Kb will have the weaker conjugate. So it's kind of like opposite day all over. So this one just depends based on for Ka or Kb. Okay, so what do you have to do with this? What's the point of all this? Why, Mr. Wood, are you making me do this? Well, first off, you have to look at a salt and say, is it 7? Is it less than 7? Or is it going to be greater than 7? So for this one, look, my parent acid would be HCl because, again, the anion comes from the acid, and then parent base would be NaOH. And since this is strong and strong, this pH would be right around 7, and it is. Okay, and again, for the next one, my parent acid would be wrong tool, HNO3. And then we have NH4OH. Okay, this is interesting. So this we know, this is strong, but this is weak. So therefore, this is less than 7. This is an acid salt. Okay, let's do another one. This would be HNO3 again. And this would be KOH. These are both strong. So this would be pH of 7. This one right here, this next guy, this comes from NaOH, right? The cation always comes. So you take the cation, add OH to it. This guy this is from a weak acid. This is acetic acid. So this would be a weak acid has relatively strong conjugate, right? So this would actually be basic. So this is a base. And then finally, we have to look up the Kas for this one. And believe it or not, I know the Kas, and the Kas are about the same for this. This is like a weird exception. So since the Kas, these are about the same, they end up being pretty much neutral. But the parents for this come from NH4OH, which is a weak base, and HC2H3O2, and they're both weak. So you'd have to check their Kas in Appendix D to figure out which one is stronger, and then that has a weaker conjugate. So that's how that goes. It's like an inverse relationship. Okay, so let's try one more just for funsies. Ready? All right, so acid or base, you look up, you think, all right, what is the parents? This one's from strong. For this bad boy, 7. Strong again, 7. Strong, weak. Okay, so strong base, weak acid. That means that this is going to be basic, above 7. Above 7. It's a base. This one, same thing. It's above 7. And finally, this last one, this is a weak base. This is a strong acid, so it's below 7. So you should be able to look at them based on the parents, or the cation and the anion, determine if it's going to hydrolyze water, which basically means will it like split water. Okay. Let's advance on. We're having so much fun today. Okay, now this is the ice problem for hydrolysis. These are the master level ice problems. So how do I know this is an ice problem? Well, first off, I know because they give me a Ka here, and anything with Ka means I'm probably gonna have to do an ice problem. Okay, so first off, we know this is going to be a base. So everybody see it's going to be a base because this is from the strong, this is from a weak acid. So the reaction, so start with the reaction, is going to be C2H3O2 minus plus water. Since these are water reactions, they hydrolyze or split water. And so what I'm going to get, and I'll draw my little equilibrium, is C2H3O2, right, plus OH minus. And there's that base part that we were talking about. This is going to be a base. So then it is just an ice problem. So we're going to do I, and it's 0.18, and then 0, 0, right? And then C stands for change. So this is going to be minus X. This will be plus X. This will be plus X. And at equilibrium, this will be 0.18 minus X. And this will be X and X. Well, so here's what we know. This is going to be, at equilibrium, it's going to be X squared, right, over 0.18 minus X is equal to, well, hold on here. See how they give us Ka? But this is a base. What do we do? Well, the first thing you have to do is you have to take and find Ka and find Kb. So you're going to do Kw is equal to Ka times Kb. So the water equilibrium constant is equal to acid times base. So if I'm looking for Kb, does everybody see it's just Kw divided by Ka? So that we can put right here is Kw divided by Ka, which is Kb right there. So now if I just solve for this expression, if I just solve everything out here, I will get my answer. But first, I want you guys to remind you one thing. Like, you're never ever going to do quadratic equations for these crazy ice problems. So you're going to get rid of x here. X, this little small amount, is going to be real dinky compared to 0.18. And the rule of thumb is you can get rid of x as long as it's, you know, less than 5%. So at the end of this, you can check the 5% rule if you like. Okay. So anyways, now what we're going to do is I'm going to move this around. So I'm going to do x is equal to the square root. So I'm just doing math here, right? Moving everything around. 0.18 times Kw divided by Ka. And that's going to be my x, or how big this is. And we're going to use this because this is important, because then we can take the negative log to find the pH for this. So let me get my calculator going here. I have my handy dandy calculator. Oh, all right, so let's do this. So we said it'd be 1.8 times 10. Oh, wrong button there. This is embarrassing. Okay, clear. 1.8 exponent. There we go. Negative 5. That's my Ka. So then we're going to do, let's see. I'm pushing the wrong buttons here. This is not good. Exponent, let's do 10 to the negative 14th. Okay. Or I think I have to do this thing. Oops. I'm not used to this, this calculator. 1 times 10 to the negative 14th. That's my Kw. Okay. I'm going to divide that by 1.8 times 10 to the negative 5th, which is my, right there, my Ka. And I get 5.6 times 10 to the negative 10th. So now that's really tiny, right? And it should be, because, you know, this isn't a very good base. Like, it's a conjugate base of a weak acid. So it's not like it's an amazing base. Okay, so we're going to take that times 0.18. 0.18 equals. So that's this number right here. We're not done with your calculator. And then I have to take the square root of that. Let's see if I can figure this out. So I could take it to the 1/2 power. I hope it didn't do this. Let's see. So I'm going to take, and then I guess I could just take this button. Yeah. All right. So I get x as equal to 0.0000. Let's see, is that 1, 2, 3, 4, 4, 1. Okay. So I'm pretty sure that this just rounded this a bunch. So you may want to type this in your calculator and just confirm this calculation. But this is the essence of it, is you just do an ice problem like we've probably done a million by this point. Okay. So anyways, since this is how much OH we have to take the negative log of this button. So you're going to type in the negative log of this, 0.001. And that's going to give you, let's see, 1, 2, 3, 4, 5. So this would give me 5. So a pOH of 5. So usually they ask for pH, so you would have to take 14 minus 5, which would be, my pH would be 9. And I know they overly rounded this on my calculator, and I think it's just because my computer did that. But the essence is the same. Just plug and chug. Solve for it. You have to find the negative log of it and all that. Okay, so these are really all the same of what we've always done, except they have one slight twist, and that twist is you have to get Ka to Kb by using this part right here. So that's the biggest thing. Okay, so I mean, I guess I can try one more. All right, same thing. All right, so if we just talk about this real quick. So this one has Ka1 and Ka2. So when we're talking about this, you have two reactions that take place, and I think this will help us to understand this a little bit better. So we have so this is the conjugate base of H2CO3. This is the diprotic. So that's why we have two calculations here. So you have CO3 minus 2 plus water, right? And that forms HCO3 minus plus OH minus. So this would be what we'd use for this guy right here, because that's the second Ka. And you can see that this is going to be the biggest amount. Like this part right here is going to cause the most, because this is the weakest acid. So it's going to have a relatively strong conjugate. So you could just use this when you do your whole calculations on this guy. So I think this is probably the easiest way to do this one. Okay, so I'm just going to kind of go for it, go ham here and figure this out here. So we're going to go CO3 minus 2 plus H2O, arrow, arrow, HCO3 minus, right, plus OH minus. And we are going to find this. So we're going to use this guy since this is the second H we lost. And really compared to the amount of this one, it's going to be relatively small. This is like 10 to the negative fourth times bigger. So it's going to be a significant amount. Okay. So then you're going to do I, and this is going to be 0.2, right? It's a strong electrolyte. This is going to be 0, 0. And it's going to be minus X plus X plus X. At equilibrium, it's going to be 0.2 minus X and X and X. So X squared over 0.2 is equal to KW divided by Ka2. And that'll give me the Kb for this guy right here. Then you're going to do X equals the square root of 0.2 times that thing, which we'll just call Kb, which that's what that is. Okay. And then whatever X is, you're just going to negative log that. And that'll give you the POH, since this is a base, and then subtract from 14 to get the pH. So rather than go through that whole calculator fiasco. So what I'm going to do is I'll tidy up this video and do the best I can with it. It's not the best of videos, guys. I'm trying, But I'll link a couple others in this one for support in case you need an actually good video. All right, I hope you're having a good day. We'll take care. See ya. Stop the recording.